Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be talking about the scientific method. So this is essentially the way that scientists look at the world to try and build up descriptions of how the world works. So what we tend to do is we try and go from uh, observations of the real world to build up a complete description of the world. Now, one of the most important things about science is that science is constantly evolving, and we're always willing to revisit our existing models and theories and try and improve them. But one of the dangers is that because of this evolving sense of knowledge, we often tend to use a slightly different vocabulary than the common world, which can lead to some confusion. So let's go ahead and talk a little bit more detail about the scientific method. So the heart of the scientific process is trying to go from empirical data, which is another way of saying experimental data or measurable data, and trying to build up a set of models or descriptions that stands up to all challenges, that is very robust. But uh, one of the things that is important to note about this is that this often means that our models get more and more nuanced because a universal description is very rare. So we tend to have very nuanced models that, in order to stand up to all special cases, and the world is full of special cases. So, how we try and build up these very robust models is using our scientific method, which is composed of four key steps. So, the first of which is we go out in the world and we make observations. Sometimes these are simple observations in a notebook. This species of bird looks like X. And sometimes these are more quantitative measurements, where I go ahead and say that this region of the world gets X inches of rainfall, or this species of bird has this color measured with uh, light measured at blank wavelength. So these can go anywhere from qualitative to quantitative. But what we end up trying to do is note certain relationships in between things. This can be things like, well, this um, this plant produces this color of flowers under these different rain conditions or temperature conditions. So we can then try and build up a hypothesis linking these two things in between, say in this case, color of plant and environmental conditions. Then we can design an experiment that tests this proposed hypothesis. And then if our experiment succeeds, we can try and go ahead and formulate a general theory or law. And we'll talk about the differences in between these in a bit. But one of the important things to remember is that your hypothesis is almost never perfectly correct. So as a result, the scientific method is almost always iterative. And this is something that is often glossed over in descriptions of how science progresses. Science is often more about failure than it is about success. As Edison said, he didn't discover a way to make a light bulb, he discovered 1,000 ways not to, because you're always refining what you find. So you go ahead and you take these observations, you make your hypothesis, a tentative explanation, you test how well this explanation holds. Sometimes it holds very well, sometimes it holds very poorly. But even if it holds very well, there's almost a little more nuance, so you try and design a better hypothesis. And you do this until it tends to hold as well as you can imagine. And what you do when you have a hypothesis or proposal that stood up to multiple tests of every possible design you can come up with, you propose a tentative theory. And in this case, a theory is a very proud statement. This is a statement that says, to the best of our knowledge, this is how the world works. However, sometimes better science, better measurement techniques come around. So you should always and continually test your experiments. It would be a very sad world if we left off our descriptions of gravity when we got to Newton. There are much better descriptions out there, but they needed better instrumentation. So always be willing to test the existing science because there may have been something that was overlooked when it was originally proposed. And this is the biggest thing about science is it's always willing to re-examine itself. So that when we do finally propose or establish a theory, it is a very strong statement. And you'll notice this that scientists almost never make a statement until they are very sure that it is true. And this is one of the things that I really do love about science. Now, one of the things I do want to try and establish is the difference in between how scientists use the word hypothesis, theory, and law, and how a typical layman does, because this often is one of the reasons why science is criticized. So, the big thing about a hypothesis is this is just going to be a prediction. So, when you'd say, uh, I have a theory how that works, what you're usually coming up with is a hypothesis. Until it's been thoroughly tested, it's not, it has no scientific standing. But that is also one of the most important things about a hypothesis is that it needs to be testable. There needs to be a way that you can falsify this statement. You can tell whether or not it holds or it's false. Now, here's one of the troubling things about science is it's very hard to say if something is true. It's just more that we've failed to prove it false. So, if we have a hypothesis that stood up to multiple tests, then it reaches that elevated heights of being called a theory, which is the current best explanation for a natural phenomenon. And in order to become a theory, it has to have made many successful predictions. And this is actually one of those important features. It can't just be that it made several, it's described the existing world very well. It actually had to predict phenomena. So when we're talking about things such as evolution, evolution has actually been able to predict a lot of what we have found to be true about molecular genomes. And as such, it's a very strong it's a very strong theory. And of course, the theory of gravity has been tested for numerous years, and it tends to keep holding fairly well. However, it is worth noting that theories are continuously being revised. And we found this being true as we go throughout all of the sciences. Most famously, evolutionary biology's undergone huge revisions and mostly improvements as we've gotten more and more genetic information. Similarly, it wasn't until very recently that we've known uh, what the key particle is that causes gravity to work, being the Higgs boson. So science is constantly improving itself, which is a beautiful thing. But most importantly, it does have to make predictions, which means that it has to explain why something happens. It has to give us a sort of causal relationship. And this kind of helps define theory. This is about as strong of a statement as you can get. Now, it's often confused in the layman public with something called a scientific law. So, a law is going to be a well tested prediction or relationship. So, laws tend to be a much stronger statement, but they often tend to be much more confined. Because one of the big things is theories should tend to be fairly universal. They should have wide applications. Laws always tend to have a lot of caveats where they hold under very specific conditions. But under very specific conditions, you tend to have a very precise relationship. So this is often a mathematical relationship. So gravity is often defined by the law of gravity, which is the idea that the force an object feels on it based on gravity is based on a constant and the mass of the two interacting objects and their distance. And we're going to be finding a lot of both theories and laws when we talk about chemistry. But again, one of the other important things about these laws is because they often are mathematical or at least hold to specific relationships, they often help define what will happen in a very numerical way. Especially when we're talking about chemistry, most of our laws will tend to be fairly mathematical, which I do apologize for. But one of the important things to keep in mind is that, especially in the modern culture, we're often having many hypotheses masquerading as theories out there. And one of the important things we need to do in order to evaluate the quality of our information is to be able to tell when we have good scientific claims. So, one of the skills I do kind of want to go over, and we'll talk more about this in class, is how we can evaluate the validity of a claim. So, here's four good criteria to evaluate a claim. The first one is falsifiability. It has to be able to be proved false. It has to hold up to a logical basis. It has to be replicable, or you have to be able to repeat the findings. And there must be sufficient evidence for the claim being made. This can be summarized in an acronym called FLAIRS: falsifiability, logic, replicability, and sufficiency. So let's go ahead and look at each of these four individually. So, can our claim be proven false? And specifically, has anyone actually tried to prove the claim false? So I want to go ahead and work through each of these various components with a very famous instance of bad science. And this was the hypothesis or claim that the measles, mumps, and rubella vaccine, or the MMR vaccine, can cause autism. So the idea here was a scientist found several cases where shortly after having received an MMR vaccine, children were diagnosed with autism. So, can this claim be proven false? This one's actually fairly easy. You find uh, a group of children who received the vaccine and a group who did not, and you find if the children who received the vaccine had more autism than the group who did not. And it actually true, and this actually is a way you can prove the system false. And yes, people have conducted this test, and every single time they found that the unvaccinated population doesn't suffer autism at a higher rate than the vaccinated one. So it wasn't. This claim was indeed proved false. However, it's lingered on. Logic. Can the does this does this claim follow a logical background? Is there a way you can go from A to B? And the conclusion has to follow inevitably from the premises. So the way I like considering this is sort of a smell test. Does something smell fishy when you hear this claim? And the MMR vaccine, there is a certain logical idea. Autism tends to present at about the same time that you receive the MMR vaccine. But there isn't a good connection in between autism and any sort of immune response. So it's a little shaky, but it could be there. And reproducibility. So all evidence in support of the claim must be reproducible. In this case, the original claim was founded on 6 cases in what appears to have been a cherry pick study that was never reproduced. So if you can't find multiple studies saying the same thing, it's probably not a good claim. Finally, the bigger the claim, the bigger the evidence you need. And it turns out that 6 cases of autism isn't enough of a claim for a vaccine causing autism. And as I said, it turns out that this is more a coincidence or a correlation, not a causation. Mostly that it turns out that you tend to see the symptoms of autism around the age of 2, which is about the same time that most children receive the MMR vaccine. So because these two things are temporarily very closely related, a lot of people saw a link where there really has never been shown to be a scientific connection. And with more and more data, with more and more outrageous claims out in the digital ecoscape, it's very important that you go ahead and examine all of them with these conditions. And we can also apply this whenever you see a scientific claim in the literature. And there's a lot of times where people like to oversell the results and they haven't taken the time to reproduce their experiments, or they try and make a bigger claim than they have data to support. So it is always worth keeping that in mind. However, one of the nice things about science is that it tends to be self correcting. And given enough time, we tend to be able to show when there is a bad study, such as people were able to refute this bad claim of autism. Unfortunately, it took several years to do so. And in the meantime, it got into this public mindset where many people believe this to be the case, despite the fact that it fails at every one of these metrics. So, next time, we're going to get back to a description of chemistry and how it helps us look at the world around us. Until then, take care.